Over billions of years since the beginning of our universe, the overall size has increased dramatically and has been expanding ever since. One of the most important and most looked into consequences of such expansion comes from the fact that almost everything we see today in the universe appears to be moving away from us, and it will continue to do so for a very long time. Hello everyone, and welcome back to the C-Squared channel. The first galaxy was discovered in 1924 when Edwin Hubble announced that our universe was not entirely localized within the Milky Way galaxy, our home, but there are billions upon billions of other galaxies scattered across the universe. Along with this, he discovered another interesting trait that was present in almost all of the galaxies he observed. They were all moving away from us. Further observations and tests later on in the century and well into the 21st century all show this very same phenomenon happening. Almost all of these galaxies and distant objects we observe are simply appearing to move away from us. Why? What's going on in the universe for this to happen? Well, this is a result of the expansion of the universe ever since the events of the Big Bang, approximately 13.7 billion years ago. Everything has been, and still is, getting pushed away as a result of this massive expansion of the universe. The best way I could describe this effect is by looking at a balloon, for example. So, let's take this balloon here, and let's place some points on the balloon, and say that these are galaxies, with our point of interest being this red one right here. When the balloon is deflated, so it's in this kind of state, we can see that all the galaxies appear to be fairly close together. So, what would happen if we start to inflate the balloon? Well, over in the next snapshot, we can see that all the galaxies have moved away from this red galaxy. And in the third snapshot, we can see that they have actually moved even further away. So at this point, the balloon itself is expanding, representing the universe that is expanding. You can see from the red galaxy that all these other galaxies are just moving away from it. What's interesting about this, though, is that it actually does not matter which galaxy you choose to observe this effect. So what I mean by this is if you chose the blue galaxy to the bottom right instead, you would see that all the galaxies appear to move away from that one instead of the red galaxy. Likewise, if you chose that big galaxy next to the red one, so this kind of pale spiral one that's face on right next to the red one, you can see that they will actually all move away from that one as well as you inflate the balloon. What does this mean for us then? Well, not only these objects are moving away from us in the universe, but if we take this into account, then this would mean that we are also moving away from everything else in the universe at the same time. Why does this happen? This is because space itself is stretching and expanding, so everything will actually end up being pushed away from each other as time goes on, rather than expanding from one individual point. So by comparing the distances to distant galaxies in this balloon model, we can actually infer something else about the expansion of the universe. By looking at the red galaxy once again, we can see that those galaxies that were initially closer move slower compared to those that were initially further away. So to put this into perspective, this edge-on galaxy right here started off as twice the distance away than this pale spiral galaxy, which is right next to the red one. In the second and third snapshots, we can see that this relation actually still holds true, so the edge-on galaxy is still roughly twice the distance away than the pale spiral galaxy, despite everything getting pushed away. So that means, in order to keep this relationship valid, the edge-on galaxy must be traveling much faster than the pale spiral galaxy to keep this ratio equal. The speeds of these galaxies can actually be directly measured on Earth, and we've been doing this for a very long time, and we can actually use these to see how fast the universe itself is expanding. In fact, it was also Edwin Hubble who first devised a way to see how rapid this expansion truly is from his observations. He indeed found that galaxies that are further away move faster than those that are closer to us. So, by fitting all of his observational data, he created this historic plot here called the Hubble diagram. In this plot, we have the speed of the galaxies on the y-axis. Amusingly, the units here are actually incorrect, but they're meant to be kilometers per second instead of just kilometers, but don't worry about that. And the distance to these galaxies is on the x-axis, which you can see is measured in a special unit called parsecs, more specifically megaparsecs. Each of the solid circles you see here are individual galaxies, though at the time people didn't know that they were actually galaxies. And the solid line represents the relation between the speed of the galaxies and the distances they're at. This line is known as Hubble's Law, and it can very simply be expressed as this equation. V is the recession velocity of the galaxy, so how fast it is moving away from us, and d is the distance it's at from us, usually measured in megaparsecs, which again I've already said is the length scale for the universe. So this middle term here, this h0 term, this is a constant that connects these values together, and it is known as Hubble's constant. It's crucial because it tells us the rate of expansion of the universe today. Now it is important to make that clear, because the expansion rate is actually always changing over very long periods of time. But for this video, we're just going to simply ignore that fact and just stick with today as, for simplicity's sake. Now there's quite a lot of dispute on the current value of the Hubble's constant, but generally around 70 kilometers per second per megaparsec is the accepted one. Funnily enough though, Hubble's initial measurement of this constant was 500 kilometers per second per megaparsec. So you can see how technology has improved on this value quite considerably. So Hubble's constant is a very important breakthrough in finally proving that the universe does indeed expand, unlike what was previously thought. Stemming from this then, can we actually see any effects or consequences from this expansion? We sure can, and to demonstrate one of the most important consequences of this, let's take a look at some galaxies for a moment. More specifically, let's look at some galaxy clusters. First up, we have the Virgo cluster, and this is literally just a huge collection of galaxies that are fairly close to us. You can see here that there's quite a mix of blue spiral galaxies and kind of yellowy orange elliptical galaxies, which are kind of these glowing blobs in here. Overlaid on top of this are stars that come from our own galaxy, so we can ignore these because of the fact that this image was taken on Earth. The center of this galaxy cluster is about 54 million light years away, so this means that light takes about 54 million years to reach us. Now on the cosmic scale, this is not very far at all, this is in fact quite close to us. Now what if we want to go to a very far distance then? Well, this is CL0024 plus 17. This is a galaxy cluster that is located over 4 billion light years away. This is about 75 times farther than the Virgo cluster, and this is a massive difference. If we compare this with the Virgo cluster, there's actually quite an interesting observation that can be made here. So unlike in the Virgo cluster, there appears to be far more red galaxies now, including some spiral galaxies which have gone a bit red as well. And even the elliptical galaxies, so the kind of blob ones that look like stars, they are normally yellowish in colour at closer distances, but now they appear to be far more orange, and are edging into a kind of a red colour. By comparing the two images, it looks like there's been kind of a shift in colour, from blue, white, and yellow, to a more yellow, orange, and red look. And that is very, very easy to notice here. This is a direct consequence of the expansion of the universe, and this effect in particular, we call it a redshift. Now there are different kinds of redshift, but the one I'm more interested in for this video, and the one I'm talking about right now, is known as the Cosmological Redshift. You see this change in colour the farther away you look, because of the expansion of the universe. I've already said that space stretches out as it expands, and I've used the balloon as an analogy for this. If I use the same analogy here, we can see that as the balloon inflates, the surface itself actually stretches and thins out so that it can occupy a bigger volume. If we look at a light ray that was emitted from a very distant galaxy, we can see that because the universe stretches out over time, the light ray also stretches and thins as a result of this expansion. So, due to this stretching, the wavelength of light actually begins to change as it travels through deep space. And if the wavelength changes, then that must mean the apparent color we see or hear on Earth will change as well. So as an example, if there is a yellow galaxy that is located some billions of light years away, the light emitted from this galaxy will be heading towards us. This light ray will be traveling for a very long time, and so the universe will have had time to expand quite a lot. So as a result, the wavelength of this yellow light that was emitted will actually stretch and thin out enough such that it eventually reaches us as orange or even red light. This then makes the galaxy end up appearing to us as orangey red instead of it being yellow as it would at very close scales. This is the key principle of cosmological redshift, and if we're looking at colors only, then we can see that this actually happens across the entire color spectrum, and not just for, colors that appear yellow or orange initially. This doesn't apply to just colors we see either, by the way, but it applies to all kinds of radiation that we can observe as well. Of course, not everything in the universe follows this redshift relation, and you can see with the Hubble diagram that there was a very loose relation that Hubble actually ended up finding. There are far more factors to include, and we can end up with situations where some galaxies and objects have additional speeds onto the ones caused by redshift. These are known as peculiar velocities, which make them move in ways that would not fit the Hubble's Law model. So as an example of such a peculiar velocity, we have the Andromeda galaxy, our closest large spiral galaxy. And in this case, radiation actually undergoes a blue shift instead of a red shift. So in this case, wavelengths of light are being contracted instead of stretching and thinning as it normally should. And so as wavelengths get shorter, they appear to be bluer. Now, what does this mean for the Andromeda galaxy? Well, if it was a redshift, then the Andromeda galaxy would be moving away from us. But because it's blue shifted, then this means that the galaxy is actually heading straight towards us. So this also means that we are very likely to be on a collision course with the Andromeda galaxy in the very far future. The expansion of the universe is something that has been of huge interest to astronomers within the last century, with the developments in working with Hubble's Law, and later into seeing how this plays into the redshift of objects. By knowing all these essentials in the behavior of this expansion, we can take a step closer into determining the true nature of the universe we live in.